All right, good morning, everyone. It is 11 a.m. It is time for Chem 1330, also known as Organic and Biochemistry for Non-Science Majors, previously known as Chemistry for Non-Science Majors. But 1310 is also Chemistry for Non-Science Majors. So had some redundancy there. Okay, well, today what we are going to do is we are going to wrap up stuff that we started last Wednesday. Then we are going to get into some organic chemistry. Now, with that in mind, I wanted to go ahead and give you a little bit of a thought update, whatever you want to call it. And so I'm going to share my screen. And this is your Canvas page. I'm going to move that. Okay, there we go. So this is your Canvas page as seen on in a web browser. Um, I've had a couple of people ask me in my other classes, hey, where are the recordings? And I want to draw your attention to this kind of matrix, this layout. This is basically your calendar. So we have meeting numbers, days, dates, graded activity for the day, material for the day, recording for the day. I will be posting your recording for the day, the one that is going on, that is being recorded, which I'm going to check and make sure. The recording that is taking place right now, I'm going to throw that on my YouTube page and link that here later today. It does take a little bit of time for the video to process and then be ready and everything like that. So I will link that there whenever that's all ready to go. You have a quiz that opens today at 12 noon, and a discussion that will open. It's going to open a little bit after class today, and that will be available for you. Let's see. Okay. Other thing, if you're ever confused or concerned, like, hey, where do I get the materials for the class? The materials for the class are going to be, I got to move the chat window. There we go. The materials for the class are going to be found in the material for the day. I'm always going to post a PowerPoint file as well as a PDF. From my experience and from most folks' experience, the one that works the best in like on a mobile device is the PDF. And that can open a little bit more easily. I think that works well, or that's really compatible, or maybe more compatible with Canvas and the Canvas app. So there is that. Then let's see. Oh, quiz number 1, which is up. It's worth a total of 10 points, 5 questions. You got 20 minutes. Available January 28th, today at 8 a.m. until February 1st at 11:59 p.m. Okay, that is maybe a little bit confusing because you've got a due date and then you got this window that it's available. The due date is Friday, 11:59 p.m. But what that means is that if you miss the due date, then you have until February 1st at 11:59 p.m. to complete it. You will be subject to a late penalty, though. Now, I mentioned on the syllabus the late penalty was 25%, but Canvas does the grading in kind of a unique way, and it's an automated grading, that part of it is automated. The deduction is automated, where it can't do, like, I can't say, hey, give people 2 days to turn this in, and if they turn it in within those 2 days, dock 25%. Instead, it has to be incremental. So what that means is that if you turn it in on Saturday, which would be January 31st at 1 a.m., then you will be docked 12.5%. What that means also is if you start the quiz at, let's say you started at 11:55 p.m. on Friday night. Because I mean, whenever I think of Friday nights at 11:55, I'm like, ooh, that's when I should take a chemistry quiz. And it takes you 10 minutes, it will be late. It doesn't matter when you start it, it matters when you submit it. If you submit it after 11:59 p.m. on Friday night, even if it's 13 seconds, 12 seconds, 1 second, there is going to be a 12.5% penalty assessed. I can't give it any sort of like grace period, unfortunately. So that's frustrating. But my point is, or at the end of the day, I think the best thing to do is just knock it out sooner rather than later. Now, with that in mind, how are we supposed to do that quiz? Well, it's only over stuff that we've already covered. So the stuff that we cover today that is new will not be on this quiz. The stuff that we cover today that is new will be covered on the quiz that is posted on Monday, which, if you're like, ooh, I'm happy to be taking a class from this guy. He seems like he's got things organized. And then you look at the schedule and you see quiz number one. You know what you've done? You've seen quiz number one, quiz number one. All of your faith and hopes in my leadership have completely fallen apart because now you're like, that bozo doesn't know that two is the number that comes after one. I do, I promise. So this is just a typo. I will fix that though. Because look, quiz three, quiz four, I know numbers. I'm good. So all that we're covering today will be on Monday's quiz. The quiz that is up as of right now is old stuff. And that old stuff is your review of general chemistry. All right. So that's our big things there. I do have some grading that I need to get caught up on in terms of discussions, and I do not want to let those fester because that will happen. I will be like, oh, yeah, I just have to do some discussion grading. Oh, I only have to do 36 days of discussion grading for 3 classes. Good planning, Joel. I don't want to do that. So there's that. And then the other thing is today we're going to have a poll question on Zoom, but everyone's getting credit for today's poll question regardless. The point today is just to kind of give you kind of practice for it. In addition to that, today I did not impose the like SSO sign in. Monday, however, is going to be our first day of SSO requirement. I'm going to share that link again, making sure that you guys know how to do that. But other than that, does anyone have any questions? You can add them to the chat. You can unmute yourself. I do have my speaker on, so I can't hear, but I've got the chat over here so I can look at that as questions roll in. And they can be about anything. But this is our schedule. This is kind of the rundown of everything. And yeah, we'll go from there. Okay, I'm going to stop. Now, the slide deck that I'm going to work on is going to be jumping off from our one from last Wednesday. So, share this right here. That's blocking that. You guys can see all of this slide. Nothing's obscured. Okay, cool. What about now? There's a big black bar in the middle of the screen. Okay, cool. I won't use that because that won't help you guys. Okay, so we're talking about the periodic table. We're talking about elements. We're talking about different pieces of nomenclature, some things that maybe you haven't heard or thought about in a little while. I have one slightly unrelated question about exams, as I have class 10 minutes before and after. Will that be detrimental in the future? My presumption, what I would do, and I'm speaking for everyone on this, if you have like a class right before this and right after that, I would just have a game plan for exam days. And I would look at my schedule and be like, okay, well, I've got history right before this. And on the day that I have an exam, oh man, I've got an exam in history. Okay, so what I want to do, and I know the history tests are all like maybe they're essay based or something like that. I need to, maybe get down to the minutia and say like, okay, well, I know exactly where I'm going to sit on test days in history because as soon as I am done, I want to hand my booklet, my blue book into my professor, and then gone. And then whenever I finish that, what I'm going to do is I'm going straight to Mochas and Javas. I've got my headphones, I've got my plan. Um, I think the question there is a little bit more, and correct me if I'm wrong, but I think that the question there is really like, do you, Joel Gray, do you expect your exams are going to take the entire class period? Joel Gray's response to that is, no, I don't. I don't write tests that are intended to be, oh, you have 80 minutes, it should take you 80 minutes. Your exams are going to be between 30 and 40 multiple choice questions. If you felt so inclined, you could do AC/DC all the way down. You can just be like, I love to rock, so AC/DC as my answer options. It's probably not going to do very well because they're randomized. But my point there is finishing the exam, I don't think is going to be that big of a hurdle. Um, I'll give you guys practice exams and practice materials so you see the types of questions that I'll ask and have a sense of, well, the like complexity and layers to them. I was asked in one of my other classes, and I'll share this with you guys. Um, how should we study? Well, I'll give you practice materials, but in addition to that, you guys have Chat GPT and or Gemini. I would take the slide decks that I give you and just throw them into there and say, hey, write a 10 question practice exam over this slide deck. So then you see multiple choice questions. And then you can even fine tune them with your prompt and say, those are good, but I wanted to be more difficult or emphasize this topic. In addition to that, you guys will have access to the recordings for this class. So you can always take the recordings, throw the YouTube link into Gemini. ChatGPT, I don't think it does particularly well with YouTube links. But Gemini, I believe, can extract information. And so you can say, here's a slide deck, here's a YouTube link. Based on what this professor talked about and the slide deck, could you give me 5 slides that are maybe the most important for emphasizing? And then while you're at it, could you write me a 30 question practice exam? That's what I would do. I think those are good ways to approach studying. Um, in terms of 10 minutes before and 10 minutes after, that's a narrow window. So I would definitely just have a sense of like, where am I going to be taking my exam? Where can I get a secure internet connection that is stable? And how should I navigate having that narrow window of time? And then along those same lines, like when you're setting up your system for taking the actual exam, you're going to have your phone set up so that you can show your screen. So you've got to account for that. So um, to answer the question, will that be detrimental in the future? In my opinion, no. But that does require some planning ahead. Does that help? And I'm not trying to be like, I don't care about your perspective. It's fine. It's easy. Take care of business. I'm glad to help you out navigating those things, but just get in contact with me because that sounds like a unique and specific issue, though not completely unique. Okay, so back to our content. So we're doing just kind of a general review or a review of general chemistry. We talked about major different subatomic particles, protons, neutrons, and electrons. Protons are positively charged, neutrons are neutral, and electrons are negatively charged. Protons and neutrons are found in the nucleus, whereas electrons are found in the space outside of that. Now, if you were to change the number of, if you were building an atom and you gave it 1 proton, that would be a hydrogen atom. If you were to give 1 proton, or if you were to make an atom with 3 protons, it's no longer hydrogen. Because as soon as you change the number of protons, you have changed the identity of that atom. So that number of protons is your atomic number. Now, the number of protons and neutrons, when you combine those, you get what's known as the mass number. Protons plus neutrons is your mass number. Now, those numbers do not have to be the same. If we look at this right here, this shows us what are known as isotopes. Isotopes are the same thing with different masses. A 1 hydrogen isotope has just 1 proton, has 0 neutrons. A 2 hydrogen isotope has 1 proton and 1 neutron. It's still hydrogen though, because it has one proton. I always kind of think about this, or three hydrogen would be a hydrogen atom with a mass of three, one proton, two neutrons. I always kind of think about this as like if I were to go to the grocery store and get a bunch of double stuffed Oreos. Well, they're all made up of, or do they have different masses? Yes, they do. If I got 1,000 Oreo cookies and I took them and put them on a very precise digital balance, I would see the mass down to the number of grams. They have different masses. Now, that's the same thing here. These different isotopes, they are all hydrogen, but they have different masses. Okay. The next thing is the atomic orbitals. And this is something that I know folks were getting a little bit mixed up on because this is kind of abstract. This is kind of weird and crazy. Now, what I want you guys to do is think about subshells as basically locations that you're going to put electrons. So electrons are outside of the nucleus, but they're not just completely random. There's some organization and order to them. I always like to draw an axis like this. Could everyone tell me what is this axis known as? If you're drawing like quadrants, that's your x-axis. What about this one? It's your y-axis. And then how many dimensions are we looking at when we look at our x and our y-axis? How many dimensions? Two. Perfect. It's helpful for me, and I hope this would be helpful for you guys as well. But I always think about video games whenever I think about this. Whenever I was a kid, the regular Nintendo came out. Santa Claus brought it for my brother and I in 1987. And to this day, my brother still is like, nobody knows where it came from. He's my older brother, and he still says that. I'm fine with that. It's like hanging on to your youth. So the regular Nintendo, Mario did this. You had two-dimensional Mario. After that came the Super Nintendo. And you know what? Then the artist started adding a little bit of shadows. And so you could see, okay, well, oh, there's some depth there. Does everyone follow me with the idea of like depth? Give me a Y or an N. Okay. So the idea is that you could look at Mario and be like, oh, okay, although he's doing this, I can tell that part of his body is deeper into the screen than another part of his body. So you guys can look into the cell that has me and say that my right hand that holds my stylus is farther from the camera than my left hand. And what you're utilizing there is what's known as the Z axis. And that's the one that kind of comes out of the page. Okay. Now I'm going to, oh, dang it. Okay. Our X, Y, and Z planes. The dashed line usually denotes going into the page. Now, when we look at these different subshells, this is just kind of giving us a visual of where electrons can be placed. So this first S subshell, that's a sphere. And in that sphere, that's where you're going to put two electrons. So S subshell, two electrons. Okay. Now, that sphere gets you two electrons as close to the nucleus, which our nucleus is going to be this origin, this intersection of our X, Y, and Z planes. It gets as close to that nucleus as possible. Okay. After that, after our S subshell, then we go on to these P subshells. Now, the P subshells are a little bit confusing, and I apologize for toggling back and forth when I didn't really want to. What I want to show you now is these P subshells. I'll go back. If you look at this one right here, it's kind of hard to see because somebody wrote over it. Ugh. We've got the PX subshell. Now that PX subshell is basically these kind of, they're not really spheres, but there are these two kind of we'll just call them globes of sorts or orbs, almost identically shaped orbs along the x-axis. If we go back, we've got the z, pz, and then we've got the py. So the py is those same shapes along the y-axis. Pz is those same shapes about the x-axis. Now, each one of those orbs, the p subshell, each one of those, px, py, pz, each one of those can hold 2 electrons. So now in the chat, could you tell me how many total electrons the p subshell can hold? 6. Perfect. Now, I want to focus in on the S and the P subshells because the S and the P subshells show our valence electrons. Our valence electrons are our outermost electrons. Those are the electrons that are most easily lost. It's also the location where electrons are most easily gained. So if we think about the S subshell and a P subshell, how many total electrons are we interested in? Or do we need to account for? 8. So if you have a full S subshell and a full P subshell, you have 8 valence electrons. Now, atoms are going to be happiest when they have 8 valence electrons. Now, if you go back and while you're studying, you look at this and you say, oh, there's the S, the P, the D, the F, I would go ahead and I would just stop right here. I would focus in on the S subshell and the P subshell because that is what is going to be most important for the content that we cover in this class, because that's where our valence electrons are. Now, with that, you've got 8 valence electrons. And you know what? There's a kind of rule that we talk about with respect to bonding and sharing electrons. Does anyone remember what that rule is? And just the name of it. I'll give you a hint. It starts with an O. And it ends with a tet. The octet rule. That was a hard word to break up and make any sense of. But the octet rule. The octet rule says that every atom wants to get to 8 valence electrons. And every atom is going to get to 8 valence electrons, maybe by sharing electrons with an adjacent atom or donating atoms to an adjacent atom. Now, when we talk about molecules and bonding, that's where this all comes in. So these right here, helium, neon, argon, krypton, xenon. Let me ask you about the S subshell. How many electrons does helium have in its S subshell? Helium's kind of tricky. It has 2, and that's all that it has. Neon, argon, krypton, and xenon, they have 2 in their S subshell, but then they got 6 in their P subshell. Helium has 0 in the P subshell. Because helium only needs 2 electrons. So it is an exception to the octet rule. Now, tell me how many electrons does tellurium, Te, have in its P subshell? 4, perfect. It's got a total of 6 valence electrons. It's got 2 in the S subshell and 4 in the P subshell. Iodine, 2 in the S subshell, 5 in the P subshell. I think that the best thing for you guys to do with respect to those subshells is focus in on, well, how many does this atom have in its S subshell and its P subshell? Those are the 2 things that I am interested in, that I want you guys to be interested in. Now, if we go over here and we talk about fluorine. Fluorine has, well, is F the same thing as F minus? Nope. F is fluorine. F minus is fluoride. Fluoride has a complete octet. That's why that has a negative charge there, because it's gained an electron. Where did that electron go? Into its p subshell to fill up that p subshell. All right. Now, in addition to that, we talked about naming ions. Ions have different numbers of protons and electrons, and that's where they have a charge. A cation is a positively charged ion. An anion is a negatively charged ion. Cations are named by the name of the element plus the word ion. Anions use an IDE suffix, that's how they end, and the word ion. For instance, the sulfur ion, the common sulfur ion is S2 minus. That is known as the sulfide ion. Polyatomic ions, you don't need to know these by name, because I would give you this whenever this comes up as a question. Covalent bonding. Now, this is what we're really interested in between atoms. Atoms are going to share electrons. Covalent bonding is one type of bonding. Another type of bonding is ionic bonding. Now, ionic bonding is a way that we can classify a bond also. Ionic bonding, I want you to think about in a couple of different ways. One way is think about it as what are the components of an ionic compound? Well, it's a metal plus a nonmetal. Okay, that's one good definition. But then we've got this electronegativity where we have basically a desire or a want that an atom has. So fluorine has an electronegativity of 4. That means if you share an electron with fluorine, you're kind of not sharing it because fluorine's going to be like, give me, give me, give me, I love that electron. And so it's a little bit obsessive. So when you share an electron with fluorine, it's not really sharing with you. Instead, it is like possessing that electron. Of course, however, you have to account for what your electronegativity is. Oxygen has an electronegativity 3.44, nitrogen 3.04, carbon 2.55. Now, how do we use this information? We use it to classify a bond. I want to come up to the top here where we have ionic. An ionic bond is where an electronegativity difference is greater than 2. Important point is that is greater than 2, not greater than or equal to, greater than 2. So if we think about the left-hand side of the periodic table having metals and the right-hand side having nonmetals, let's talk about sodium fluoride, NaF. If we were to classify that by what are the components, we would say that is an ionic compound. And by virtue of it being an ionic compound, it's going to have an ionic bond. Give me a 7 in the chat if you agree with that idea. Okay. Now, let's talk about this in terms of the bond. Well, let's talk about it in terms of its bond and the electronegativity differences. The electronegativity differences 4.0 and 0.9. What we want to do is figure out the difference between that. Well, when you're doing this sort of thing, your electronegativity difference is going to be what's known as an absolute value. So you could say 4.0 minus 0.9, and that's going to be 3.1. You could also do 0.9 minus 4.0, and you'd come up with negative 3.1. Well, it's an absolute value. So we'd put these kind of uprights around that negative 3.1, and that would give us a difference of 3.1. What is the absolute difference between these? We're not looking at negative or positive. An electronegativity difference is always going to be positive because it's an absolute value. So we have an electronegativity difference between sodium and fluoride of 3.1. How would we classify that magnitude of a difference? Well, 3.1, is that greater than 2.0? It is. So we would classify this bond as an ionic bond. Now, does that go hand in hand with what we already said? that it was an ionic compound? It does. So I always kind of think about an ionic bond as through the thinking about a covalent bond. Oh, you're sharing electrons. And then I think about the degree of this, the magnitude. Our electronegativity difference, it is so, the electronegativity difference is so great that the sharing isn't really sharing. It's so electronegative that it's ionic. Now, for our others, we have a nonpolar covalent bond and a polar covalent bond. A nonpolar covalent bond is where the electronegativity difference is less than 0.5. Oh, but what if it's 0.5? Then that is not a nonpolar covalent bond. That would be a polar covalent bond. So give me an N for nonpolar, P for polar. What about N and O? Is that going to be an N or a P? Absolutely. Our difference is 3.5 minus 3.0. Difference is 0.5. So that would be a polar covalent bond. Oh, but what about carbon nitrogen? Same thing. 3.0 minus 2.5 is 0.5. Oh, but what about CP? Perfect. That would be a non-polar covalent bond. So if you would just not bear with me, but maybe this is just how I speak, but it has always been easier for me to think of these electronegativities and think about polar as rather than thinking about like North Pole or South Pole of a magnet or something like that, I think of polar, non-polar. Why is that? It's just been easier for me because I think about you've got sharing of electrons, you got sharing of something, and there's a tug of war. Okay. Well, the one that is more electronegative is going to be pulling more than the other. And if I get an email from somebody's English professor and they say, uh, Joel, did you know that puller is not a word? I will say, no, I didn't know that. I don't know if it is. It might be a word. I haven't looked it up. I haven't taken the time to do that. This is just easier for me to think about. Okay, so our electronegativity difference is going to help us classify a bond. Now, when we kind of apply that, well, electrons are negatively charged. When something has a large concentration of electrons, it's going to be more negative. There's more negativity around it. So we classify it with this dagger symbol here. This dagger has a positive end and an arrow, which kind of represents the more negative end. We also use this delta symbol. This is a lowercase delta. Positive, delta, negative. The more negative part is going to be this delta negative. So that's just a way of illustrating what a molecule looks like. Is it more negative or is it more positive? Now, the last way that we can visualize this is with this right here. And this is known as an electron density map. The blue region, and really this is just monitoring where are the electrons? Where are they more likely to be found? Blue indicates few electrons, and red indicates more electrons. Now, Lewis structures for polyatomic molecules. Okay. Poly atom, polyatoms, multiple atoms, polyatomic molecules, water, ammonia, methane. These are all polyatomic molecules because, well, they have multiple varieties of molecules. Water, hydrogen, and oxygen. Now, oxygen tends to form two bonds. Ammonia, well, nitrogen tends to form three bonds and a lone pair of electrons. These are known as lone pairs of electrons compared to this right here, which is a shared pair. Now, a shared pair of electrons can also be drawn like this. And then sometimes, though not very often, you'll see it drawn like this. Are we going to have to remember all the A and E molecules? Not right now. When we get to organic chemistry, which is later today, I'll show you the ones that you need to know. But spoiler alert, there's some simple rules and that'll make it a little bit easier. Okay. Now, numbers of bonds of covalent bonds formed by different elements. This isn't something to memorize, but instead what I would think about is, what does this relate to? This relates to valence electrons. How does it relate to valence electrons? Well, let's think about it. How many valence electrons does fluorine have? 7. If fluorine has 7 valence electrons, how many electrons does it need to get? 1, in order to have a complete octet. How can it get that 1? Well, it can get that 1 electron by maybe sharing with another atom, or maybe there's an ionic or there's an atom that will donate it. But if it shares one of its electrons and another atom shares an electron with it, now all of a sudden it has a shared pair of electrons. How many electrons does this shared pair represent? Shared pair. 2. A pair. You're absolutely right. So whenever we have a single bond that represents 2 electrons, that's 2, 4, 6, 8. Okay, so now let me rephrase this and say an atom. Geez, Joel, your handwriting is embarrassing. No, it's not. It's really good, actually. Atom with 4 valence electrons. How many bonds? How many covalent bonds will it form? Okay, so that means that atom is bringing 4 electrons itself. It needs to get to a complete octet. So it rolls up with its own 4 valence electrons. How many bonds will it want to form? If each bond corresponds to 2 electrons. Add your answer to the chat. I got the private message of 4. You're absolutely correct. Now, think about it like this. Another way to visualize this is I'm just going to draw an X for my hypothetical atom. 1, 2, 3, 4. Those are the 4 valence electrons that this atom X rolls up with. Could everyone give me a P in the chat if you follow that, or any number if that doesn't make sense to you? Okay. So now, let's say that we have Y as an atom with 1 valence electron. Actually, you know what? I'm not going to go with Y instead. I'm just going to go with hydrogen. Hydrogen, we know, has 1 valence electron. Hydrogen, one valence electron. X is going to see this and say, hey, you know what? We should share. And hydrogen's going to say, well, you know what? I don't need 8 valence electrons around me, but I do need 2. So in this situation, is hydrogen getting what it wants? Y or N to the chat? It is. Okay. Is X getting what it wants from this interaction? It's getting there. So, you know what I'm going to do is I'm going to convert that from two dots. I'm going to draw the hydrogen a little closer, and I'm going to draw it like this, like that. Is everyone good with that? Wire N to the chat. That's one shared pair of electrons. Now, this depiction right here, how many electrons does this X atom have? It's got one, two, three, and then a shared pair, which brings us to five. So has X reached its octet? No, it hasn't. But if we had another hydrogen, that's looking good. That's looking good. This is looking good. So if something brings four valence electrons, it's going to want to form four bonds. Does that make sense? Give me a wire N to the chat. Okay. Now, you probably also remember, let's say, you know what I'm going to do is you probably remember some other things about drawing molecules from 1310 that are relevant and are going to be very important whenever we talk about and we get into organic chemistry. I'm going to go back to my molecule X. Brings four valence electrons. And I'm using carbon because carbon brings four valence electrons and it forms four bonds. What if we had an oxygen? Oxygen brings in two, four, five, six. Does oxygen want to reach an octet with eight electrons around it? It does. So oxygen is going to see atom X and say, oh, hey, we can share. So oxygen's like, that's a good deal. And X says, yeah, that's a good deal for me too. And then we can share these as well. And X is going to say cool, and O is going to say cool. So now we've got something that looks like this, something known as a double bond. This corresponds to four electrons. So now, could you tell me in the chat, how many electrons does this oxygen basically see? Or how many does it have for all intents and purposes? 8. It does. Now my X has this and this. So X only sees 6 so far. What if he had H and then another H? Does X have 8 electrons around it? Give me a wire N to the chat. It does. Does oxygen have 8 electrons around it? Yes, it does. Okay. So could you give me on a scale of 1 to 5? 1 being, oh, I've got this completely conquered, and a 5 being, I'm still struggling with this. Where are you with this particular, the number of covalent bonds that something is going to form? And you can send it as a private message if you want. Okay, seeing ones. Good. All right. So now we're going to go ahead and proceed from there. Practice drawing Lewis structures. We could, that's not really real. That's not going to be on the quiz. What I think we're going to do is we're just going to focus primarily on getting to organic. At the heart of all of this is how many valence electrons does something have? You're going to have a periodic table on your exams, and you'll have a periodic table on quizzes whenever it's relevant. Okay, so next up is chemical equations, balancing a chemical reaction. You have to know what are the reactants and what are the products. Left-hand side has your reactants, right-hand side has your products. When I say left versus right, I am talking about in the context of that arrow. So the words or the language that we typically use would be something like carbon plus oxygen yields CO2. Now, if you look at this, this is balanced because there's one carbon right here, two oxygens, and then there's one carbon, and then two oxygens. So that's completely balanced. That is all accounted for. Now, if we look at this right here, N2 plus H2 yields NH3. If you have one N2, only one of them, and one H2, will you be able to produce NH3? The answer to that is no. The reason for that is you need three hydrogens. So how could you do this? Well, what if you have H2, H2 plus N2? Could you get NH3? You could. If you did that, you'd be using up nitrogen, and then this hydrogen, and then a third hydrogen. You could get to NH3, but you'd have something left over. In a balanced chemical reaction, we are going to have nothing left over, and we're going to reach a ideal ratio of reactants to one another and to our number of products. Now, I think the example that is a good one to use would be something like hot dogs. If you buy a bag of hot dog buns, you're going to get 8 hot dog buns. If you buy a pack of hot dog franks, you're going to get 6 franks. Those numbers don't make any sense. You're not going to take those to a cookout and then somebody's going to be like, finally, you brought 2 extra buns. This is great. Instead, they're going to be like, why didn't you just buy more hot dogs? And you say, well, I didn't want to. And then they're going to be like, okay, well, let's take this outside. And you're going to say, we're already outside. And they're going to be like, okay, well, let's settle this. You say, this really escalated very quickly. I don't know why we need to fight, but let's do it. Let's go to HEB and get the correct number of hot dog buns and franks. What we need to do is figure out where we need to go with this. And so we're going to say, okay, well, we got 6 franks, we got 8 hot dog buns. If I bought another pack of franks, then I'm going to have 6 franks, bringing me to franks. 12 franks. Okay, so now I got 12 and 8. Okay, well, that still doesn't work. Okay, so now I need to buy another pack of buns. So now I got 8 buns. Now I'm at 16. Well, that doesn't work. I'm at 16 and 12. So then I'm going to buy 6 franks. And that's going to get me to 18 franks. Is everyone following my math? Give me a number 5 in the chat if you are. And so I'm just going back and forth, volleying these two back and forth, because I know that a hot dog is 1 bun, 1 frank. Okay, so I've got 18 franks, 16 buns, 8 more buns. That gets me to 24 buns. And then 6 more franks. And that gets me to 24 franks. So what I would need to do, the perfect ratio for this is 3 packs of hot dog buns and 4 packs of hot dog franks. And that will get you your optimal product of 24 hot dogs. Okay. Now, when it comes to our next part of chemistry, that's really an important or a vital review piece. That is the concept of a mole. Now, a mole is just a defined number. And I can say this, and I've said this many, many times in my life, and it's just a tough thing to wrap your mind around. I've said, well, 1 dozen is 12 items. If I had 12 coffee mugs, then I have a dozen coffee mugs. Go both ways. You have 5 dozen coffee mugs, you have 60 coffee mugs. So the thing that I'm talking about can vary, and the number of them can vary. A mole is just a number of things. So 1 mole of something is 6.02 times 10 to the 23rd of that thing. That's tough to think about because that's such a large number. Now, in addition to that, moles of things have different weights. So a dozen pencils, a dozen nails, a dozen roses, a dozen eggs, these are all going to have different weights. Likewise, well, could anyone tell me in the chat, what does one egg consist of? Crack an egg, what do you find inside of there? A yolk and an egg white. Those are the building blocks of this. If you think about a car, if you think about a car being the body of the car plus four wheels, one car is equal to body plus four wheels. Now, if you had 1 mole of cars, how many moles of wheels would you have? And let me rephrase this and put like round numbers on it. If you have a dozen cars, how many wheels do you have? Add it to the chat. 48. Perfect. Because each car has four wheels. Okay. Now let's do this again. 1 mole of cars. You have 6.02 times 10 to the 23rd cars. How many wheels do you have? Well, for each car, you have four. Another way of putting it, yes, four times that. So you could say you have 4 moles of wheels. Does that make sense? Could you give me a Y or an N to the chat? Okay. Okay, great. All right. So then the last thing that I'm going to talk about with respect to the kind of review stuff, and we'll get into more review stuff as it comes up, but I just wanted to spend a little bit of time generally reviewing, is when you look on the periodic table, you're going to see a couple of different numbers. One is the atomic weight of something. 1 mole of carbon has a mass of 12.011 grams. This whole number 6 is going to be the number of protons, which is equal to or the same as the atomic number. 1 mole of copper, if you look at that on the periodic table, 63.55 grams. So right here, we've got 1 mole of copper. Right here, it's 1 mole of sulfur. This is 1 mole carbon. I always like to think about these things as if you have 5 grams of carbon, do you have less than 1 mole, exactly 1 mole, or more than 1 mole? If you have 5 grams of carbon, you have less than 1 mole. And then you could take that in terms of number of atoms of carbon. Well, 5 grams of carbon is less than 1 mole of carbon. Okay, now what we're going to do is we are going to switch over. I'm going to end this slideshow. Does anyone have any questions on this before I do click end slideshow? Okay, I'm going to go ahead and end the slideshow. I'll keep those notations. I will save this. And then we are going to jump into organic chemistry. So we're switching over to the other slide deck for the day. And this one's not too crazy long. Organic chemistry is all rules. I think, however, it's not rules that are really number centric. If you remember valence electrons and how many bonds something forms, you're going to be in good shape when it comes to organic chemistry. Now, I am sharing my screen and I am sharing the right screen. to better understand biochemistry and to better understand chemistry, we need to take a deeper dive into organic chemistry. Um, okay, now I'm going to launch our first poll question. If you are accessing your poll questions on a mobile device, you might have to look for the little three dots, the ellipse, that you click on that and it'll bring up a more menu if this did not automatically pop up. And this is just kind of like, how do you feel? Have you ever heard this term before? Are you familiar with it? I'm going to give you guys about 1 minute. We're at 23 seconds up. 10 seconds left. And you go ahead and end the poll. Okay. So 22 folks participated. Everyone's getting credit for this one. The most popular answer, chemistry of carbon-based molecules. That's the best definition. I couldn't find it on my phone, says a private message. You're going to look for, and we'll have one more opportunity later in this class period. So, but you want to look for three little dots, and underneath those three little dots is the word more. You want to click that, and that's going to bring up like a menu, and it's probably going to say polls, and you're going to click that. Is there anyone who has any advice on how they found it, or did it automatically pop up? If you have advice, add it to the chat, send it as a general message so everyone can see it. Okay, so organic chemistry. Organic chemistry is defined as the chemistry of hydrocarbons and their derivatives. Hydrocarbons are a class of compounds. Why is it doing this? It's weird. Oh, that's what I need to do. Hydrocarbons are molecules that consist of hydrogen and carbon. Not too much of a wild stretch there or anything. Is that sharing? No, it's not sharing. Okay. Sorry, I'm having weird issues with my tablet right now. Hydrocarbons and their derivatives, so molecules that are made up of hydrogen and carbon, and those that have other things added to them. Of tens of millions of known chemical compounds, over 95% are compounds of carbon. Carbon is unique in that carbon atoms can bond to each other to form long chains and rings, and a carbon atom will always bond 4 times. So what this is saying is that you can have some molecule that looks like this. Whereas the same thing is not true with atoms like nitrogen. So if you have nitrogen, you're not going to have nitrogen, 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 and so on. So this is kind of unique. Now, these are the commonly found atoms, or the other 4 commonly found atoms bound to carbon are hydrogen, oxygen, nitrogen, sulfur, and your halogens. Most of what we're going to talk about deals with these 3 right here. And then that's because those are the major molecules in biochemistry. Now, well-known examples of organic compounds include ATP. Give me a 7 in the chat if you've ever heard of ATP. If you've never heard of ATP, ATP stands for adenosine triphosphate. That's really kind of referred to as the energy currency of the cell. And that's produced in the powerhouse of the cell, the mitochondria. Caffeine, that's what this is right here, this doubly ringed structure. And then last but not least, this guy over here, glucose. Okay, so these are some major molecules when it comes to organic molecules, and important molecules when it comes to organic molecules. Now, properties of carbon. How many bonds can carbon form? 4. What's the electron configuration of carbon? Okay, so this goes back, well, we've got 1s2, 2s2, 2p2. Now, if you're looking at that and you're thinking, oh man, well, you just talked about S and P, and I did, and I stand by that. If you add up the outermost or the last written S and P subshells, and then add those exponents, it's going to be four. Four valence electrons, four bonds. What type of structures can carbon molecules form? Well, carbons can form linear molecules. They can form planar molecules. They can form tetrahedral molecules. We talked in 1310 a little bit about geometry and visualizing molecules in 3 dimensions. Now, one thing that we didn't really touch on, but is important to know about, is when we're discussing valence electrons, specifically when we talk about carbon. Carbon has 2 valence electrons in its S subshell and 2 in its P subshell. Now, give me a 5 in the chat if you'll follow me on the journey that an S subshell, a spherically shaped subshell, and a P subshell, that kind of doubly balloon looking one, that those are different shapes. Give me yeah, perfect. I want you to kind of go, okay, I understand it. S subshell has one particular shape, and a P subshell has a different shape. Now, in order for atoms to be shared, they have to be found in what's known as a hybrid orbital. So, could you tell me if, let's say you were an explorer and you went to, I don't know, you're sailing in the middle of the ocean. We'll go with the Pacific Ocean. And then all of a sudden, something came up, it surfaced, you're in your boat, and you see a dinosaur head, and you're like, oh my gosh, it's a dinosaur. It's crazy. And then that thing continued to surface, and below its dinosaur head was the body of a killer whale. You might think, wow, that is crazy. I have never seen that. A dinosaur killer whale. What's the word that you would use after that to describe this thing? It's made up of only these 2 things. Dinosaur, killer whale. The word I'm looking for starts with an H. A hybrid. Now, would you be able to like capture that thing and make your own SeaWorld that put every other SeaWorld out of business? Totally. Because people would come from miles around to see the dinosaur killer whale hybrid. Well, this is almost as interesting, where we have an S subshell and a P subshell that they kind of merge and they make something that's what's known as a hybrid orbital or a hybrid subshell. Okay. Now there are other hybridizations. An SP hybrid orbital is what it's known as, an sp2 and an sp3 hybrid orbital. These are all similar but different from one another. Now, what's important to know about this is specifically focusing in on the sp3 hybrid orbital. This is 1 part S subshell and 3 parts P, hence sp3. Now, could you guys tell me an sp2 hybrid orbital is 1 part S? How many parts P? Perfect. 2. Okay. Now, what I want you guys to think about with respect to this is to think of an sp3 hybrid orbital as being made up of 4 things total. 1 S and then P, P, P. Give me a emoji in the chat if you follow that. Or a letter in the chat if, wait, what? Okay. Now, there's a little bit of a trick or a game of sorts. And what I want you guys to think about is you can be asked questions like, what is this molecule's hybridization? And I want you guys to be able to answer that question. That question's kind of tough. Obviously, I have not written a molecule, but what is this molecule's hybridization? And what I want you guys to do is we're going to start out with the molecule CH4. Okay. CH4 is a hydrocarbon, and the hybridization, the question is really always about the central atom. What is the hybridization of this molecule, but more specifically, this carbon's hybridization? Could you give me a 5 in the chat if you understand when you ask about a molecule, we're asking about one specific atom's hybridization? Okay, I got one response there. And I think maybe as we work through this, it'll make a little bit more sense. When I'm asking what is the hybridization of this carbon within this molecule, I want you to look at it and say, well, really what I'm being asked is how many things is this attached to? Tell me in the chat, how many things is this carbon attached or bound to? 4. Okay. So I want you to use that number as your way of looking back at hybridization and saying, okay, well, if our central atom is bound to 4 things, it is sp3 hybridized. SPPP. So now, if I were to say CH2CO, and I want to know about the hybridization of this molecule, I'm going to draw it. And this is the sort of question I want you guys to be able to answer. I will give you the structure of something. I'll say, what's the hybridization of this carbon in this molecule? And then you say, before you answer that hybridization question, look at that and say, all right, well, here's one thing that the carbon's bound to. Here's another thing the carbon's bound to. And here's a third thing. Even though this oxygen has a double bond, it is still considered one thing. So my question for you guys is, how many things is this central carbon right here bound to? Add it to the chat. 3. Perfect. So if when something is bound to 4 things, it is considered sp3 hybridized, what do you think it is whenever it's bound to 3 things? sp2. Okay. Last but not least, what about this molecule right here, carbon dioxide? What do you think the hybridization of carbon dioxide is? Thinking specifically of that central carbon, sp. Perfect. Great. Wonderful. Okay, so what I want you guys to take away from this is whenever you're asked about hybridization, I want you to pinpoint how many things is that carbon bound to. If it's bound to 2 things, it's sp hybridized. If it's bound to 3 things, it's sp2. If it's bound to 4 things, then it's spp or sp3 hybridized. Now, that is like, what? Huh? It is kind of wonky and crazy. But if you follow those kind of rules and that kind of idea, how many things is it bound to, you're going to be in good shape with that sort of question. Now, if we move on from there, I would say that that's one of the tougher things to understand about organic chemistry. Carbon is unique because carbon can do sp, sp2, and sp3 hybridization. Not every atom is capable of doing that. That's why we bring that up. Now, major categories of organic compounds. There are hydrocarbons. Those are carbon and hydrogen-based molecules. They're alcohols, phenols, ethers, esters, aldehydes, ketones, carboxylic acids, amines, amides, alkaloids, and more. Now, we're going to get into these individually. We're going to start out with hydrocarbons, then we're going to look at aliphatic compounds, and we're going to specifically look at alkanes, alkenes, and alkynes. Now, I want to jump ahead to the stems for organic molecules. When it comes to the naming of organic compounds, what we're most interested in is, well, how many carbons does that molecule have? If a molecule has but one carbon, it's going to use the stem of meth. Two carbons, eth, three, prop, four, bute, five, pent, six, hex, seven, hept, eight, oct, nine, non, and 10, dec. So the name decane, at this point in time, and not that it's necessarily committed to memory, but if I said, hey, I found this molecule known as decane, how many carbons does it have? You guys could piece that together. 10. Okay. Well, now, as it turns out, I was able to break decane into a octane and ethane. Now, does the math on that make sense? Are there any carbons that are magically appearing? No, this makes sense because octane has 8 carbons and ethane has 2 carbons. Could you make octane and nonane from decane? Could you do that? No, you couldn't. Because octane has 8, nonane has 9. That's a total of 17 carbons. You're not going to be able to magically make that. Okay, so these stems, meth, eth, prop, bute, pent, hex, hept, oct, non, dec. That's the extent of the numbers that I want you guys, or that we're going to need for this class. If something has 11 carbons, does that have a different stem? It absolutely does. Are you guys going to need to know that for this class? You're absolutely not. Now, there's different ways to display chemicals. So you can use what's known as the molecular formula, a condensed formula, a complete structural formula, and what's known as the skeletal structure. What is shown here, these are all representative of the same molecule. Now, looking at this and thinking about the previous slide, could you tell me what is the stem that we would use for this molecule, or for any of these molecules for that matter? Count up your carbons. 1, 2, eth. Yeah, eth. So this has eth. This has eth. This has eth. All right. Now, for aliphatic hydrocarbons, our alkanes, alkenes, alkynes, and cyclic hydrocarbons, those are what we're interested in. Now, in order to do that, in order to look at those, and yes, we have about 5 minutes left in class. I haven't lost track of it completely. We did do one poll question. Okay. And yeah. So one carbon alkane is known as methane. Ethane is a 2-carbon alkane. Propane is a 3-carbon alkane. 4-carbon alkane is known as butane. Now, one of the things that I want you to recognize about all of these molecules is the total numbers of each atom. These are nothing but carbons and hydrogens. One carbon, H4, CH4. Okay. Ethane, C2H6. Propane, C3H8. Butane, C4H10. Now, the formula for these can be calculated. N represents the number of carbons. And to calculate the number of hydrogens, you would say 2 times N plus 2. So if you had a 40 carbon alkane, what that molecule is going to look like, or sorry, let me rephrase that. The molecular formula for that is going to be C40H. Could anyone add that to the chat? 82. Could everyone give me a Y if that makes sense, or an N if you want me to do another example? Okay. Now, what's important to know also about alkanes is that the carbons are always saturated. What? Who? Well, what that means is that there are no double bonds. That means every single carbon has its maximum number of hydrogens added to it. And let's look at this. Okay, here and here are carbons that are at the end of the overall chain, the 3-carbon chain. There's this carbon and this carbon. They both have 3 hydrogens bound to them. This one right here, well, that's got a carbon and 2 hydrogens. Okay. So your carbons that are inside the chain, that's going to have, well, 2 carbons added to them. So this one is an internal carbon. This one is an internal carbon. Now, I'm going to launch this. This is our last poll for the day. This is where we're stopping. We're going to pick up with alkanes the next slide. That would be slide number 10. We're going to pick up with that on Monday. What I want you guys to make sure that you can do is that you can answer a poll question and try to work this one out. I think these are 2 kind of good test questions. So the first one is, how many carbons does a molecule of cyclopentane have? Oh man, cyclopentane? And then next is, how many hydrogens does hexane have? This is an alkane, so try to deduce that. Hydrogens, not carbons or any other. As soon as you've answered that, thank you guys very much for coming to class. I hope you have a good one. Your discussion will be posted a little bit later today, and I will see you guys on Monday. I've got office hours starting in about 10 minutes, so if you want to drop by, you're more than welcome to. All right, everyone. See you. And I'm going to leave the poll up for a little bit so that everyone can answer. I am going to end the slideshow. Like this. So 5 participants, and I can give you about 10 more seconds to answer. And then out. Yeah, 10 more seconds. That'll be a full 2 minutes on the poll questions. And end. All right. Have a good one.